Okay, so welcome back. What did we learn in the last lecture? What we learned was we had studied the Schottky junction between metal and a semiconductor. We also highlighted the differences between Schottky and ohmic type of contacts. What kind of characteristics you expect from a device if you have a Schottky contact or versus an ohmic contact. We had studied the band diagrams for aligning the Fermi level between metal and n-type semiconductor, metal and p-type semiconductor. And I told you that for making a p-type semiconductor, an ohmic contact to a p-type semiconductor, you will need a metal with a large work function, whereas for making an ohmic contact with n-type, you might need a metal with lower work function. So the choice of work function can dictate what kind of IV characteristics you are going to get. If you form an ohmic contact, you will get a linear IV. If you form a Schottky contact with a barrier, then you will get a characteristic which is very similar to that of PN junction diode like behavior. You will have a forward turn on, and then you will have a reverse leakage which is very low, and eventually it will break down. Okay. So all these things we have learned. Also I had highlighted in last lecture about the importance of forming a metal contact to semiconductor, right. We have studied the depletion depth, the built-in potential, the Schottky barrier. We have derived the many equations which are very similar to an abrupt one-sided PN junction essentially. So today we shall quickly finish the Schottky junction treatment by going through the derivation of current. What is the magnitude of current that flows through a Schottky junction when you forward bias or reverse bias it? Once we know that, then we will be able to correlate with PN junction and compare which device is better, a Schottky diode or a PN junction diode, and we will see what is the current magnitude in both case, for example. Okay. After that we will start with a new topic, a real transistor called BJT or bipolar junction transistor. So before we start that, we will finish up the entire things that we need to do for Schottky junction and compare it with PN junction. Okay. So we will come to the whiteboard. If you remember in the last class, we had derived the expression for the different parameters in a Schottky junction. If I draw this as the Fermi level of the metal, and then there is a Schottky barrier like this here. I had solved also a numerical, if you remember, right. This is conduction band, this is Fermi level, this is valence band, and of course as you know this is the depletion width, and this is the built-in potential. This is the Schottky barrier height, which is dictated by the built-in potential plus this gap here. Okay. Please remember that this region is flat, this is the flat, there is no neutral, this is the neutral region, and the EC minus EF is constant here, but is not constant here. Okay. That please remember that. Okay. And this is a Schottky junction to an n-type semiconductor. You might as well make an ohmic contact to an n-type semiconductor by having the work function of the metal lower than the work function of the semiconductor. You can make a ohmic type contact, but here we are talking about Schottky type contact, right. So I told you whenever you apply a forward bias, it means you are applying a sort of a positive bias on the metal with respect to, you are putting in positive bias with respect to the semiconductor, you are putting a positive bias, in which case in the forward bias electrons from the semiconductor will be transporting over this barrier to the metal here, and this barrier height, this barrier will keep reducing by QVBI minus QVA, and the depletion also will reduce by W minus some delta W, just like a PN junction, because the electrons are essentially coming over this barrier. Okay. So it depends on the energy that you are supplying, also it depends on the temperature, by the way. Okay. Similarly, when you have the reverse bias junction, okay, when you have reverse bias junction, then you are going to apply a negative bias in the metal with respect to the semiconductor. You are going to make the depletion width longer and the barrier even larger, like this. Okay, the barrier will be larger and electrons will be pushed from metal to the semiconductor side, but this barrier height is there, which is not going to change with bias. So you will have very little current, very low leakage current, and until it breaks down, right. So the objective now is to determine the current, to determine the magnitude of the current through the across the metal semiconductor junction. Okay, MS junction, metal semiconductor junction. If you recall, in a PN junction ideal diode, the current density across the semiconductor PN junction is given by J naught e to the power QVA by KT minus 1, where this was the applied voltage, and this J naught was something like QDN by ln Ni square by this is n type, so Na plus dP by Lp Ni square by Nd, if you remember that, right. And this Ni square depended on band gap, it was proportional to e to the power minus Eg by Kt. So all these things to remember, right. So the in case of metal semiconductor junction, this treatment is a slight different because there is no diffusion or drift diffusion sort of a whole electron minority carrier junction is not formed here. It's a junction that is formed between metal and a majority carrier. Electrons are majority carrier. There is no minority carrier injection like electron hole. So the treatment and analysis is slightly different. Okay. What I mean by that is that, let's take this junction and let's focus on this again. Okay. So this is a Schottky junction. Okay. Now let's do one thing first. This is the depletion. So I am defining the depletion. Okay. This gap EC minus EF, that will dictate the equilibrium concentration here. Equilibrium concentration in the neutral region is N naught, which is equal to ND. And if you remember, N naught, that is given by ND, that is given by the conduction band density of states exponential of EF minus EC by KT. Okay. That is the equilibrium concentration, that is constant from here to here. Okay. Now at this, if I consider this as x equal to 0 and this is x axis, so this is x equal to WD, this is the depletion region, right. In equilibrium I am talking about, so there is no light shining, there is no voltage I am applying. At this point at x equal to 0, you see the conduction band is here, the conduction band is here, the Fermi level is here. So the difference between the conduction and Fermi level is huge. So of course the material is depleted, and that is why there are much fewer electrons at x equal to 0 here at this point here, right, because the conduction band EC minus EF at the surface, EC minus EF at the surface, this is at the surface, right, this is EC minus EF at the surface, which is huge, much larger than EC minus EF at the bulk. Bulk is deep inside the semiconductor here, which is corresponding to equilibrium concentration, but this EC minus EF gap progressively increases. It progressively increases, right. So at the surface it is the maximum here. So the electron concentration at this surface will be the minimum. It is depleted. There are very few electrons, but still there will be few electrons compared to this part, but you will have some number. Okay, it's depleted. So if you look carefully, compared to this in the conduction band, this conduction band over here has an energy which is QVI higher. So this energy, whatever you have in conduction band here, if you add that to this value, you get this particular conduction band. So in other words, this energy is the excess conduction band that is bending, the excess bending that has happened in the conduction band as it goes from bulk to the surface. So if I say that electron density at this top is N top, that is the free electron concentration is depleted, matlab it's very few electrons are there. Okay. If I call this as N top is equal to the electron concentration at this point, then if you recall a band, the electron concentration changes exponentially with respect to the band. So if the band has changed from this value to this value, this particular gap, then the electron concentration here will be electron concentration here, which is N naught, times exponential of the negative of this, exponential of negative of QVBI by KT. Please take a moment to look at this. I told you once that even if you have any profile like this of conduction band and the Fermi level is suppose constant, then if at this point the electron concentration is N naught and at this point the electron concentration is N1, you look at the difference of the energy between these 2 points, this gap which is say delta V. So the electron concentration at this point will be lower compared to the concentration here N naught by e to the power minus delta V by KT. Okay. That is that it goes exponentially as the variation in the energy band. So this is the gap that has that is the extra gap that has arisen here, right. This is the extra gap delta V that has arisen here. So and because the Fermi level has gotten that much far away, so basically the electron concentration will decrease by the exponential of that amount. That is why this here the electron concentration at the top will be electron concentration here times exponential of minus this. Okay. Why am I telling you all this? Because we are going to derive the current expression, but as of now we are only talking about equilibrium. So how can you talk about current expression? Very good. So what we will do is that I will consider a small forward bias voltage that is applied. So if we apply a small forward bias voltage, then there will be a small difference in the Fermi level. So this is your metal Fermi level, okay, and suppose this is your conduction, this is a semiconductor Fermi level EF, this is the semiconductor Fermi level, quasi Fermi level. So, this was the, suppose the phi b, this was the barrier that does not change at all, okay, the barrier does not change, and this has become like that, this has become like that. So, your bending has now reduced by q v b I minus applied voltage V A, that has reduced by that amount, okay, that has reduced by that amount. Okay. So, there is a difference Fermi level between this, the difference in the Fermi level here and here is actually q v A, that is the applied voltage you have given, the depletion rank also has shrunk by some amount. Okay. So, now at this is x equal to 0, and suppose this is the new depletion with W dash W d, just think about it. Okay. So, at this interface at x equal to 0, at this interface the electron concentration is n top, okay. The electron concentration is n top, which is given by electron concentration here, which is n naught into exponential of what, this gap, which is now reduced because of application of a voltage. So, minus q V b I minus V A by, this is Boltzmann time T. Okay. All right. So, now that is your electron concentration at the top. Okay. But this n naught in equilibrium here, of course, that is equilibrium, I mean not, that is far away in the bulk, is given by n c, which is the conduction band density of states, exponential of what, E f, and matlab this is the quasi Fermi level there, minus E c by k b t. Now, if you look carefully, this Schottky barrier height phi b is given by this, which is q v b I minus V A plus this plus E c minus E f n plus this amount, this plus this will give you the whole Schottky barrier height. So, that amount is q v A. So, this q v A, this q v A is gone. What remains here is q v b I plus E c minus E f n is equal to phi b. So, your E c minus, or you can say E f n minus E c will be equal to q v b I minus phi b. Now, this value you can put it here, right. So, what will happen then? Let us come to the next page. So, you can put or I can put right here only. So, if I write this equation now, okay. So, it will be n naught equal to n c e to the power, instead of that I will put this q v b I minus phi b by k t, okay, q built in voltage minus phi b by k t, this is t, okay, n c. So, I can use this expression now. What will that I write? I will write that as, let us go to the next page. So, n top, the electron concentration at the top is given by n naught, right, into exponential of minus V b I minus V A. So, that is given by exponential of minus q V b I minus V A by k t, right. Instead of n naught, what I will write is, I will write this V b I minus phi b. Okay. So, I can write n c e to the power q V b I minus phi b by k t. So, I will add this up also, minus q V b I plus q V A by k t. Okay. So, this will go away. So, your n top, electron concentration at the top will be n c exponential of q V A minus phi b by k b into t. So, this is your electron concentration is the top, in the top. It is very small number because your applied voltage is very small, whereas the built in the Schottky barrier is pretty high. This quantity is very low actually, that is why we call the film to be the top W d to be almost depleted completely. Okay. That is why it is very low concentration. Now, when you have a metal semiconductor junction, in equilibrium the electron trying to come from here to here is exactly balanced by the electron tendency coming from here to there. We call that as, say, I metal to semiconductor current, which is basically the same from both sides. It is balanced, and that is why there is no current flow in equilibrium. The moment you have non-equilibrium, you have applied a positive forward voltage, it becomes low, no? It becomes low by that amount, right, by q v b I minus V A right. So, the electrons will now have a more tendency to come. So, they can come now. So, that is why this is coming. Now, this current that will flow across this junction, essentially that current, if I write that current as I, that is actually proportional to the flux of carriers that will cross this, and the flux of the carriers depends on the velocity with which they are moving times the charge density. The charge density at this interface at x equal to 0 interface is n top. So, in other words, the current is proportional to the velocity of the electrons that are moving across this junction, okay, times the carrier concentration at this interface, which is NC exponential of QVA minus phi b by KBT. This is your current that is proportional here, and of course, there is a conduction band density of states here. This will be like the thermal velocity. So, you can actually you can replace this from experiment this proportionality constant that you have, your velocity times NC exponential of what was that was QVA minus phi b by KBT. Okay, the proportionality constant can be actually obtained experimentally, and even some other more theories there. So, what you will club down the velocity, you will club down the density of states. It has a lot of temperature dependence, this also has a lot of temperature dependence. So, the way, and of course, it will depend on the area also, area of the current, the diode or the device. So, eventually it will look like A area into some constant called Richardson constant times T square, okay, exponential of QVA minus phi bt by KBT, okay. It will look like that, except that there is, you have to subtract 1. Do you know why that 1 has to be subtracted? I will come to that. There has to be a, actually this is not correct, let me come to this a little later. So, there is a proportion, I will come to that quickly. So, there is a proportionality term here that will depend on many temperature and other things. So, you see this depends on a voltage applied VA. If the voltage applied VA is 0, then the current will be proportional to A velocity NC e to the power minus Q phi b, or Q may not be there because this is energy, minus phi b by KT. You see, this is the current that is there when there is no applied voltage. But we know that in a metal semiconductor junction, if there is no current, if there is no voltage, that is applied, which is V A equal to 0, then the total current across both sides should be equal, and that is why that should be 0. Okay. So, when I say V A equal to 0, I get this current. I mean that this current actually tries to go from both metal side to semiconductor side and from semiconductor side to metal side, and they balance each other. So, the total current in the device at equilibrium at V A equal to 0 will also be 0. So, what is this current? This current actually is the magnitude of the current that tends to flow from metal to semiconductor and from semiconductor to metal, balancing each other, resulting in net 0 current. So, if I want to apply a forward bias now, okay, if I want to apply a forward bias, then for finding out the net current from semiconductor to the metal, the net electron flow from semiconductor to metal will give you a current in this direction, right. So, to find out the net magnitude of the current there, we have to subtract this current from the total forward bias current. You see my point? This current is basically the current that exists between the metal and semiconductor metal, they balance each other, and that is why the total current is 0. The moment you apply a forward bias and you reduce the barrier, and you have more, now you have current flow. The moment you apply forward bias, that extra current, what will, the total current that you get, from that you have to subtract this current to get the actual true current flowing. Okay. So, what it means is that, whenever you apply forward bias current, so the Fermi level will not be equal now. So, whenever you apply forward bias, so this is suppose the metal Fermi level, okay, this is the Schottky barrier height, and this is the semiconductor Fermi level, quasi Fermi level. The barrier has reduced now, right? The barrier has reduced, QVBI minus VA, right? QVBI minus VA. So, this quantity has to be subtracted. This quantity I, which is proportional to area, velocity NC e to the power minus q phi b by kt. This component needs to be subtracted from the actual current, the current that should be flowing. Only then you will get the true current that is flowing, right, because this is always there which is balanced actually. Okay. So, the actual current under bias will be, now this proportionally constant can be removed. I told you that is area times some constant called Richardson constant, and velocity and this all have their own their temperature dependence and other things. So, you can find it out. So, this will be T square, actually a temperature square dependence will come, because the conduction band density of states also depends on T to the power 3 by 2, velocity also has its own dependence. So, it will be air T square e to the power, okay, minus q phi by kt, okay, minus q phi b by kt. So, in total forward bias you will have a term, extra term, no, that is e to the power q v a by kt, that is your applied bias, minus this term you have to subtract, a r t square e to the power minus q phi by kt. As I had told you many times, this term is basically the background term that has to be subtracted, because this is equal and opposite in the semiconductor metal junction. Okay. This to this and this to this is equal, and that is this. Okay. They balance each other, but the moment you apply forward bias, more electrons will come here. So, this current has to be subtracted. So, eventually the current will look like A Richardson constant T square exponential of minus q phi by kt e to the power q v a by kt minus 1. Okay. And if you apply reverse bias, then this quantity will become negative, e to the power minus negative quantity becomes very small quickly. So, this quantity is almost becomes minus 1. So, this current will be the current, this component essentially this component will be the current that will keep flowing in the reverse bias. So, in the reverse bias, and this is I, this is V, in the reverse bias the current that will be there is very small, and that current will be equal to this component. Okay. At 0 there is nothing, at reverse bias this will be there, and eventually it will break down. In forward bias, as you can see, in forward bias you can see that in the forward bias this is the total current which is exponentially dependent. So, exponentially dependence goes like, this is 0 actually, sorry, just put here I V. So, this will break down, very small current. So, this is the forward bias characteristics. Okay. It is exponential increase, just like a PN junction, except that in PN junction this is J naught, in Schottky barrier junction this is this. Okay. So, this is a temperature, also another dependence is T square here. Okay. So, you see in forward bias this regime you have the exponential dependence, in the reverse bias you have a constant current given by this. Of course, there will be generation recombination current, if you remember generation recombination current, whatever we did for PN junction also will apply here. So, it will slightly keep increasing here, because the generation recombination current also adds a small component, but otherwise this component is your reverse bias component only. Okay. So, in reverse bias the current should be constant, and this should be the value from where you can actually find out phi b if you know the temperature, but in reality it is slightly increases. So, how do you find out, one of the things that you find out from this temperature dependent, from this IV characteristics, you are given a metal semiconductor junction. For example, you are given a metal semiconductor, this is N type and suppose this is metal here, you are given a metal semiconductor junction, you are asked to find out the Schottky barrier height phi b. So, what you do is that you do the IV, right, you do the IV, say this is room temperature. Okay. You recall the IV equation, I equal to, or the J current density. So, area is taken into account, is some Richardson constant, that is constant T square exponential of minus q phi by kt into e to the power q v a by kt minus 1. Okay. So, if you take log of the current or current density versus T square, this T square you bring here, then it will be proportional to minus q phi by k into 1 by T at a constant V A. So, for example, you take temperature dependent IV, suppose this is 300 Kelvin, then you go to a slightly higher temperature. So, it will be something like that, slightly more higher temperature, it will be something like this, you slightly go another higher temperature, you keep going like this, right. At any particular VA, small VA, say 0.8 volt or something, at small VA, you look at the current here, you look at the current. So, that current is this J. You divide, this is say 400 Kelvin, this is 350 Kelvin, this is 325 Kelvin, this is 300 Kelvin, you can take many temperatures. So, that current is that current at particular VA. So, you know the VA, so you know this at different temperatures you have this different current is there. You plot with respect to J by T square. and if you plot it with respect to 1 by t, because this is the relation, then you will get a slope like this. What I am saying is that if you plot log of j by t square versus 1 by t, so that means temperature is increasing this way, then you will get these data points that fit like this. It will be a straight line, and the slope of the straight line will be minus this quantity q phi b by kt. From there you can no, actually t will not be there, sorry, minus q phi by k. So from there is no t here. From minus q phi by k you can find out the Schottky barrier height phi b, right. Sometimes of course you want to keep the VA also, so it will be minus VA like this. So from there you can find out the slope. So this kind of transport is called thermionic transport. Okay, this Schottky transport that is happening here is called thermionic transport, because it's a, you know, it's an injection across the thermal barrier. Like with the thermal injection, it is across a barrier. So this is the conduction band, this is valence band. Electrons are coming here, electrons are coming here. This is a barrier. The electrons are crossing purely because of thermal energy, right. So this is called thermionic transport, and thermionic transport has this signature that log of the current versus t square. If you plot it with respect to 1 by t, the slope gives you minus q phi b by k. Or it can sometimes be q phi b minus t. So you actually can, you know, VA, that is a particular VA you are looking at. No. So basically from the slope you can find out the barrier height. So this is a very fantastic way of finding the, if you make a metal contact to semiconductor, if you do temperature dependent IV, then you can find out the Schottky barrier height at the metal semiconductor interface. This is a very beautiful approach to finding the Schottky barrier height in a metal semiconductor junction, and any new research that people do with different kind of materials, carbon nanotubes or molybdenum disulfide, these new materials, new structures, they always try to see if the transport, you know, the current voltage characteristics, is it like a Schottky nature, is it a thermionic. So this signature gives you that it's a thermionic Schottky kind of a transport, okay, and then you will be able to extract the barrier height. So this is the beauty of this you know, thing. So now we have pretty much finished up the Schottky barrier junction, except that we have to take into account one small thing, that, you know, the Schottky barrier total equation is given by area, some Richardson constant, times t square e to the power minus q phi b by kt into e to the power, this is multiplied by q a v by kt minus 1 ideally, okay. This is a Schottky junction, and a PN junction, this is given by q dn by ln ni square by Na, for example, plus electrons are moving there. So dp by lp into ni square by nd into again e to the power qva by kt minus 1. So this term is the same. Rest all terms don't matter so much, it's exponential term that matters. So here ni square is there, that ni square actually can be written as e to the power minus eg by kt, right. So I can take this also out, q e to the power eg minus kt dn by ln into 1 by a plus dp by lp 1 by nd. Of course with ni square there is some other terms like square root of nc, nv, and all these things don't matter so much, it's exponential. So the Schottky barrier reverse current, so I'll erase this, okay. This is the reverse current in both Schottky barrier junction and PN junction. You see in Schottky barrier junction the reverse current depends exponentially as minus q phi b by kt. So more the Schottky barrier height, lower is the leakage. In PN junction the reverse leakage depends as this, which is exponential of minus Eg by kt. Now if you look in the Schottky barrier junction, this is Schottky barrier, for example, this is your Schottky barrier phi b, right. Your Schottky barrier, this phi b, is always less than the band gap. You see the band gap is much larger. Schottky barrier is very little, is half of that, maybe less than that compared to band gap. So this quantity will be always larger compared to this quantity, because e to the power minus Eg. So if I take silicon, this will the PN junction leakage will go as e to the power minus 1 by 0.026, that is the band gap, because this term is there, no. But in a Schottky barrier junction to silicon it might be 0.4 eV, for example. So that will Schottky barrier will go as e to the power minus 0.4 by 0.026. So see, e to the power minus 1.1 will be always much smaller than this. So the reverse leakage in PN junction is always much lower than the reverse leakage in Schottky. Even if Schottky junction and PN junction characteristics look similar, which is, you know, it goes like that, but the reverse leakage in a PN junction is much many orders of magnitude lower than the reverse leakage in a Schottky, because in a reverse leakage in a PN junction depends on the energy of the band gap, e to the power minus band gap, but in a Schottky junction it depends on e to the power minus 5e, which is the Schottky barrier height, and that is always less than the band gap. So the leakage in a PN junction is much lower. So if you want to block more voltage, if you want to low leakage, if you want to have a high breakdown device, instead of Schottky you should go for PN, because PN will give you lower leakage. However, a PN junction has both electrons and holes, and whenever there are holes move slowly because their mobility is much lower. But in a Schottky junction like this, there is no hole. It is purely electron which is majority. Electron is majority. So a Schottky junction is a majority carrier device. A Schottky junction is a majority carrier device because there are no holes. Electrons, so electron only. Whereas a PN junction is not a majority carrier device. It is both majority minority, like it's a bipolar device, right? And because of the holes, things become slower. So a Schottky diode, because there is no hole to slow down, can be very fast. You can switch on and off much faster than a PN junction diode, which could be slower than a Schottky diode. But PN junction diode will give you higher breakdown. So you have to trade off whether you want more breakdown or you want to more speed. So it's a application based decision that you have to take into account when you do PN junction and Schottky junction. Okay. So with that we will conclude today's lecture, and we will also conclude Schottky junction. So today we had learned about everything that is there on Schottky junction. We have derived the current expression, the current voltage characteristics. It's just like a PN junction, except that there is extra t square term. So the thermionic transport has a log of j by t square versus 1 by t, gives you that slope, straight line whose slope is basically the barrier. So from that you can find out the Schottky barrier height. And I told you that because the Schottky leakage depends on exponential of barrier height minus barrier height, whereas PN junction leakage depends exponential on minus band gap, and band gap is much larger than Schottky barrier height. That's why leakage in PN junction, reverse leakage in PN junction is always many order of magnitude lower than the leakage in a Schottky junction of the same material. But PN junction will be slower than a Schottky junction because you have both electrons and holes tend to slow down the device. A Schottky junction is a majority carrier device because there are no holes, for example, if you make a contact to electron. It's a majority carrier device, so it can be very fast, but its blocking capabilities would not be as good as PN junction. It cannot have as high breakdown as a PN junction. Okay. So with that we will conclude Schottky junction completely. We have covered PN junction, we have covered Schottky junction. We are completely ready to study the next topic, which would be transistors. Okay. So we'll meet you in the next class with the topic of transistors. Thank you.